All right, so let me explain an artificial neural network on this hypothetical example, right? So here we have the first layer is input. So this is my input layer, input. So this is layer 1. Then we have layer 2 is our hidden layer. And layer 3, so yeah, hidden layer is this whole thing. It has 3 neurons. And layer 3 is my output. So generally speaking, every fully connected artificial neural network, it has L layers. Out of them, 2 are input layer and output layer. So L minus 2 are hidden layers. So whatever is in between. Now, to each neuron, except for the input layer, so we associate some parameters and some so-called activation functions, right? So here the activation function is sin z, here the activation function is z squared, and here is the error function. Erf of z is what is the probability. Well, it's basically associated with the cumulative density of standard normal distribution. In any case, so it is just an example, right? So, and then there are some linear transformations, right? So here is the linear transformation. So this neuron, whatever it gets from the input layer, right? So it multiplies the first input by 0.3, the second input by 0, and adds negative 4.1. And then whatever the result of this operation is, it plugs it into the sign, which is the activation function, and that's going to be its output, right? So, and its output goes into the third layer. So, right? So input 1 is x1, input 2 is x2. So the hidden layer consists of 3 neurons, right? So the first neuron, the activation function is at f of z, and the weights are beta 0, negative 4.1, beta 1 is 0.3, and beta 2 is 0. So similarly for the second neuron, so it has a different activation function, and again 3 weights. And sorry, this should be the third neuron. Third neuron. The activation function is the error function, and so there is a different combination of weights. And the output layer, right? So the activation function is the sigmoid, and again, so we have some other weights. And notice that since the output layer, it sits on top of layer 2, which has 3 neurons. So which means that so every neuron in layer 2 is supposed to construct one of the inputs for the output layer. So this is why the output layer has 3 betas, not 2 betas like the hidden layer, but 3 betas, right? So because it has 3 inputs. So the number of inputs in the output layer is 3. So 1, 2, 3. So in order to be consistent, it is supposed to it must have 3 betas. Right, so here is an example how we calculate, right? So if x1 is 50 and x2 is 80, right? So the first thing that we do, we are going to compute the output of the hidden layer, right? So first we are substituting 50 as x1. So now this is going to be 50, x1 is going to be 50, x2 is going to be 80, and x2 is going to be 80, and then we are going to compute the result, right? So, and then so we are applying the linear transformation to this vector 50, 80, and the output of this linear transformation is going to be inside each neuron is going to be some number, and then we're going to just pass it into our activation function. So then we're going to apply our activation function, and this is going to be the output, so right, of our hidden layer. So it means that this minus 0.995 comes out of the first neuron. See, this number 628849 comes out of the second neuron, and number 1 comes out of the third neuron, right? And then we are plugging them into into the linear transformation that happens in the output layer, and then we are applying the sigmoid function, which is the activation function in the output layer. And this 0 is going to be the final output of the entire model. Okay, so this was a hypothetical example. So here is a more realistic example. So here we are going to have layer 1. It's going to be our input layer. Then we will have 3 inputs, three hidden layers, and layer 5 is going to be the output. So the dimension of the layer is just the number of neurons, right? So we have 2 neurons here in layer 2. So we have 3 neurons in layer 3. We have 2 neurons in layer 4. We have 1 neuron in the output layer, which is layer 5. Yeah, so the output layer usually has 1 neuron, but there are exceptions. Well, and the input layer, so the dimension of the input layer is just the number of predictors. So it's always just going to be P. Okay, now theoretically we could use any activation function, so your favorite function, whatever, logarithm, anything, we can use as activation function. So, but in practice, we always use this so-called linear rectifier for hidden layers and the sigmoid function for the output layer. So, by the way, people started using this linear rectifier in 2011, so not so a long time ago. So before that, everyone just used sigmoid rectifiers in all the layers, including the hidden layers. But then, just 9 years ago, people realized that, come on, it's not very good. So, and there is a better choice, and this led to a drastic increase in the speed of training artificial neural network. So the switch from using the sigmoid to using the linear rectifier, which is, it's also called ReLU, rectified linear unit, it led to a bit of, together with some other clever improvements in algorithms, so it led to the artificial intelligence revolution, essentially. Right? So in 2000, so that began in early 2010s. And one of the components of this artificial intelligence revolution was this clever idea to use the linear rectifier instead of a sigmoid as activation function for hidden layers, right? So basically, it happens that training is much faster with a linear rectifier than it is with sigmoid. Yeah, so there are other choices. So if you, I don't know, if you just read the Wikipedia page on ReLU, rectifier neural networks, so you will see that there do exist a lot of different options, but unless you know better, unless you somehow know that some other choice of an activation function is just more suitable for your problem, I think the easiest thing to do is just to go with the default one, and the default one is this rectifier. Right? So the rectifier, simply the rectifier, its output is x whenever x is positive and 0 whenever x is negative. Well, z. If z is positive, then ReLU of z is z itself, and if z is negative, then ReLU of z is 0. Okay, so now how does it calculate the final output, right? So first, the layer 2, which is the first hidden layer, it receives the input, and the input is 4-dimensional. So x1, x2, x3, x4 is the input, and then it applies a linear transformation, right? So, and this vector that sits here in parentheses is called z2, and yeah, so notice that the superscript here is 1 rather than 2. I don't know why, but this is kind of traditional in deep learning theory to denote the parameters associated with layer k are denoted with w and b with superscript k minus 1. So I guess maybe because they somehow represent the transformation that happens between layers k minus 1 and k. Okay, so and then the output of this second layer is just called as a vector is just A2, right? But then if you want to specify, then you can write down its specific components. So then we have layer 3. So the vector that is here is the vector Z3. So it is a 3-dimensional vector, and this vector is A3. It is also a 3-dimensional vector. So the A vector is obtained from the Z vector by applying our activation function to every entry of our Z vector. So here is, this is what's going on in layer 4, and this is what's going on in layer 5, which is the output layer. So notice that here, the activation function is not R, it's not the ReLU, but it is sigmoid function instead. Okay, so here is a quiz for you.